In December, we always have issues that should have been fun somehow. Now, many of you will already raise an eyebrow and wonder how mathematics will fit into here. So today my task will be to bring you closer to mathematics and to show that math does not have to be boring at all. Do not expect any sidewise differential equation, but be open to the following topics. In order to prepare myself for the webinar, I went to customers and employees and asked, what comes in your mind when I say math in the labs? There was only one answer, rule of three, so I thought, great, then this will be short fun. Of course, there is a lot more when you have time to think about it. I want to show you how I would write down the rule of three on a sheet of paper. If you like it, feel free to copy it. The rule of three is always preceded by a question. So, for example, for my Christmas dinner, I need 400 grams of meat per guest. I expect 12 guests. How much meat do I have to buy? So first I write down what I know and mind that same information is on the same side. So person here, grams here. The wanted or the value I search about is getting an X. So I draw a line between the same here and here, and I get a fraction then, and I try to put the X in the counter. So I just switch both sides, and while doing this, same units, here person can be reduced right away. I write an equal sign between the two sides, and each side is multiplied with 400 grams, and voila, I have to buy 4.8 kilograms of meat. This reduce of unit is a very important step in the laboratory arithmetics. Therefore, it makes sense to talk about units more intensive. Please note the colored 7 base units of the International System of Units. Kelvin as the unit of temperature, second of the time, meter of a segment, kilogram of mass, candela, the light intensity, mole as amount of substance, and ampere of current. All other units, I just added some you perhaps know from the lab here, are a combination of these 7. Except for Kelvin and second, all units follow the decimal system. Kilogram is a special unit because the base unit already contains a 1000-fold factor, though the kilo that is. To express parts or multiples, these prefixes are used. For every number here in the potency is a special prefix, so I just entered the most common ones used in the lab to have an overview. These have their origin in Greek, Latin, Italian, and even Scandinavian, and describe the defined power of 10. So if the power is positive, like in the case of kilograms, you can easily shift your point or commata 3 digits to the right. So 1, 2, 3, and you would have 1000. If it is negative, for example for micro it's -6, then you can shift your minus to the left side, and 6 times you do that, so 1, 2, 3, 4, 5, 6, and you have 0.5 times 0, 1, let's say, grams. Conversions are often done wrong in the lab daily work, so the prefixes can always be written as numbers, so kilo as 10 to the 3, milli as 10 to the -3, and so on. This can be done, and this is one of the first rules, this can be done in the numerator or the denominator or in both. It's just your choice what you want to do. So if you have 1 milligram per milliliter, you could write these milli as 10 to the minus 3. And you can shift them to the front of the fraction and multiply it with the number before the fraction quite easily. And with shifting of the commata, you can you obtain 0.001 grams per milliliter, so you easily convert it in this direction. The same goes for the denominator. So if you want to get rid of this milli here, you want to have milligrams per liter, then you write the milli as 10 to the minus 3. But attention now, you have to use the reciprocal when you write it in front of your fraction. So from 10 to the minus 3, you would have 10 to the 3. Then you can calculate that, shift the point to the right side, 3 digits, and you would have 1000 milligrams per liter. You can also use this second rule to convert. So this rule says that multiplying two numbers with the same base, so in this case it would be 10, then the powers here are added. If the power of these added ones is 0, then this is automatically 1. So it does not depend how your basis is, so it could be E or 137 or whatever. If it is to the 0, then it is always 1. By writing the numbered prefixes in front of your units, then shifting them in front of the fraction. Be aware that here you have to use the reciprocal, right? Then you can easily go this way and shift these two 10 bases together and add their potencies. And if you calculate this, you get 10 to the 3, so minus 3 plus 6 is 3. Then you get 1000, and you convert it from milligram per microliter to grams per liter. But this is working also the other way round, so backwards in this rule. It is no problem in mathematics that you just multiply something with 1. So this is not bad, this is okay. So if you multiply with 1 here, then going this rule, you can write this as 10 to the 0, and then you choose, for example, a minus 6 and plus 6. So you add this here because it would be 0 and at the end 1. And then you can shift these numbers to the numerator or denominator just as you like, but always be careful that you use the reciprocal. So if you decide to take this 10 to the minus 6 here, the 10 to the minus 6 up to the numerator, then you have left 10 to the plus 6, and if you want to do it in the denominator, then it's a reciprocal. Then you can either write the number as prefix again, like in this case, so 10 to the minus 6 is micrograms, or you even scale down further. So from the 10 to the minus 6, you can describe this as 10 to the minus 3 plus minus 3, so always be aware of the minus and pluses here. You can divide this again via this rule, so you have a 10 to the minus 3 times 10 to the minus 3, and then again you can write one of those as prefix, so it's getting milliliters, and afterwards you can shift this number in front of the fraction and you would have 2000 micrograms per milliliter and convert it grams per liter to micrograms per milliliter. So please play with the rules and you will see that converting is not difficult at all. With few exceptions, the temperature is given in degrees Celsius. So 0 degrees is the temperature at which water is solid, and 100 at which it is a gaseous form. in thermodynamics, one wanted to introduce an absolute 0 point, so a point where no molecule is moving, and you can imagine that this is only reached in the universe. So 0 Kelvin was measured as minus 273 degrees, and as the Kelvin scale and the degrees Celsius scale are both linear, you can easily convert the two scales like it is shown here. Theoretically calculated, this is the highest temperature that ever was reached by the Big Bang, and this is called the Planck temperature, just to mention. In the US, Fahrenheit is still used, so this is this scale. Again, water was used as reference, but it was mixed with sea salt. Therefore, the boiling and the freezing temperature was shifted, and the scale does not behave linearly. So you only have the possibility to remember this formula to calculate the degrees Celsius to Fahrenheit. The time scale below a second behaves decimal. So for example, you have a millisecond. But above, scales are used that historically derived from Babylonia, Egypt, and the Maya. As basis served the orbiting sun or her shade, so in a sundial. Therefore, we have this circular form of our watches and clocks and else, and its division in the day to 24 hours, the hour in 60 minutes, and the minute in 60 seconds. In America and in Britain, inches and feet are still used instead of meter. So this can be scaled and converted easily because it's linear. So 1 inch are these centimeters and 2 inches double the amount and so on. And I think you know that obviously the origin in foot lies in the average length of a foot in the times when it was invented. Today I think this value would be some different because people getting bigger and bigger. But let's go further into the chemistry now and to our lab arithmetics. I want to talk about the mole. So the mole was invented by Wilhelm Oswald here, and he said that 12 grams of carbon have 6 times 10 to the 23 molecules. This is the so-called Avogadro constant. It is important to know for us in the lab that if you weigh the molar mass of a substance, you have exactly 1 mole. The molar mass of a substance can be found online, certificates of analysis, or the best way, the periodic table of elements. For example, here with silver, you have this number below the symbol and the name. It's 107.9, and this means that you just weigh this number, 107.9 grams, and you have 1 mole of silver. So now imagine you ordered something at our online shop at Serva, and you ordered magnesium sulfate, and you get it, and you read in your lab book, use water-free magnesium sulfate for your buffer. And you said, oh no, I have not ordered water-free, I have ordered the heptahydrate. Damn, what to do? But after this webinar, we stay cool because we can calculate the molar mass of this heptahydrate. This would be 2 times 1 gram per mole for hydrogen and 16 gram per mole for oxygen times 7, and you get 126 grams per mole of crystal water you have inside this ordered product. So if you have an aqueous solution, the crystal water does not matter at all. You just have to think about weigh 126 grams more than written in your lab book, and everything is fine. talking about the lab books, very often you find in protocols that solutions are described as percentage VV and percentage WV. So what does that mean? V means volume and W means weight. The percentage in front indicates automatically that it refers to 100. So this is the word centum in Latin. That's where it's come from. So I have entered here the SE units. So if you want to do to 100 parts, so 100 milliliter, then you have to be aware of the unit. So if you mix milliliter, then you have, of course, use milliliter of the second solution, and if you have milliliter here, then it is grams afterwards. And this results in our two samples. So in the first example, if this is in your lab book, 5% WV of sodium chloride, you dissolve 5 grams sodium chloride in 100 milliliter water. And in the second, this is the volume equation. So if you have 5% VV of ethanol, then you use 5 milliliter ethanol in 100 milliliter of water. At this point, I would like to mention the golden rule in the lab, which has at the moment nothing to do with mathematics, but please never fill up. Measure before it, so measure solution A and B, and then just add it. If you don't do that, sometimes molecules of different solutions fit together, and so the volume will be lower than the two single solutions. And if you fill it up to the volume you want to have, then the ratio of these two solutions would change completely. When dissolving solid and liquids, the terms molarity and molality are quite often used. So for a molar, you have 1 mole dissolved in 1 liter whatever. So if it's always a golden rule in the lab, if there is nothing else mentioned, you just take water. And for molality, 1 mole is dissolved in 1 kilogram of whatever. But that does not mean that this kilogram is a solid product, but it's a liquid. But why should you weigh a liquid? You could measure it. Well, this makes sense, for example, for glycerol, because glycerol is quite viscous and would stick to the sides of your pipette, of your glass, whatever, and you would never get completely out the liquid of your measurement apparatus, and therefore you weigh it to get rid of this error. The molarity and molality is for sure the same for water. But why? Because 1 liter of water is weighing exactly 1 kilogram. But this only fits for water, so beware of that. For acids and bases, normality is always used, so it's a number n, mostly written. So it refers to the number of protons or hydroxide ions. Examples are here in hydrochloric acid and in caustic soda. You just have 1 molecule of these both, so 1 normal is the same than 1 molar, and 1 normal of the base is also 1 molar. But this changes when you take a look on the sulfuric acid. Here you have 2 protons. So that is meaning that 1 molar would be, because of these two normals, or in this case 1 normal then would be half a molar. The most common formula used in the laboratory containing molarity is this one here. You should remember it, write it down, or just print out this sheet. If you want to know how much sodium chloride, here you have to weigh to obtain 100 milliliter of a solution with 50 millimolars of sodium chloride. So what you do, you just multiply the molar mass with the desired molarity and the desired volume. My tip is convert the unit previously before putting them here into the formula. I write down here the correct units. So for example, here you have nothing to change, gram per mole, you just enter 58.44 grams per mole. But then the molarity, you want to have 50 millimolar, but as unit in the formula have mole per liter, so you can describe this in advance as 0.05 mole per liter, and the same goes for volume. You should have liter, here is milliliter, so it's 0.1 liter. If you do that right, you have no problems at all with converting some units, and you get 29.22 milligrams you have to weigh. To calculate the molarity of ready-made solutions or liquids, the density can be of help. So you easily can use this formula here. So this is the molarity, and if you divide the density with the molar mass, you get the molarity quite easy. In this example, I want to show you how you go along with it with hydrochloric acid. So it's a concentrated one, so 37%. And you can go, for example, to Wikipedia and you get the molar mass of hydrochloric acid and you get the density. Here you have to be careful to care about the temperature, the pH, and so on. And of course, of the percentage of the solution. So Wikipedia is nice, very kind to us, and have 37% solution density as value already here. So you take this one, and then you divide. Be careful about the units. You have to convert the centimeter to liter, and you have 1,190 grams per liter divided by the molar mass, 36.46 grams per mole. And for the hydrochloric acid, this would be 12 molar. But why 12 molar? Because you don't have 100% of solution, you only have 37%, so this factor needs to be inside of this equation additionally, then everything is fine. The dilution factors and mixing ratios often cause confusion because of the same spelling or writing, but I want to explain it the right way and using such a cleaner or an agent, cleaning agent, as example for it. On the cleaner you find 40x concentrate, so it's 40-fold concentrated, and this fits to the dilution factor of 1 to 40. But if you turn around it and you look what you have to do, then they always say just add such a small cup here or one part of this into yes, a bucket or 5-liter water or whatever, but the main thing is you have to add it. So 1 part plus 39, even if in some lab books you find this expression as 1, 2, and that is not right. This is made wrongly since decades, but well, to make this more clear, I have made a table to make it more understandable. So if you have a dilution factor of 1 to 1, this would be 1 part in 1 part, and this is of course pure. If you have 1 to 2, it's 1 part in 2 parts, so you have to add 1 part and 1 part water. And if you have 1 to 500, then it is 1 in 500, so 1 plus 499 parts of water, for example. Here's an example of a classic dilution. You see that it contains information that you could calculate easily with the rule of 3. This is not a problem at all, but there is a tool that is widely taught in technical assistance schools and makes sense for questions, tasks that are a little bit nested, just like this one. what do you want to do? You have two solutions. It's solution A with 35 grams per liter salt A in it, and solution B with 15 grams per liter salt B in it, and you want to mix those two to have a solution of 20 grams per liter total salt. And for this problem you can use the Pearson Square. You see right away that it is somehow a graphical support of the mathematics. So you have this cross here that helps you or guides you through your mathematics. And first, you note on the left side of the cross your adducts, or your what you have, let's say, like that, and in the middle you write down the goal. So you have 35 grams per liter solution A, 15 grams per liter solution B, and 20 grams per liter of your mixture. Then you subtract the values crosswise. So you do 35 minus 20 is 15, and on the other side it's 50 grams 15 minus 20. So normally you would get minus 5, but as you have these lines here, this is meaning don't care about minus or plus, it's always plus, then it is 5. You add those two, so 5 plus 15 is a sum of 20. So what does this say? Quite easily, for example, if you would mix these 5 parts, 5 milliliters of solution A, and 15 parts, for example 15 milliliters of the two solutions, you obtain 20 milliliters of a 20 grams per liter solution, and you easily finished your equation very fast. The only unit I want to address is Katal, due to the frequent request in our tech serve. So if you buy our collagenase, for example, you always get this Katal value. The unit describes the conversion of 1 mole of an edict by an enzyme per second. Please note that this value is dependent on many factors, so please read the manual quite well, that you are sure to have the right Katal. These Katal values are quite high in normally, let's say, and due to this high Katal values, you find another unit has been established, and this is the so-called international units, in short IU, or also U, depends on the manufacturer. And this factor is just a conversion of the units. So instead of mole per second, you use micromole per minute. You get a lower number, so a shorter number, it's more comfortable to work with or to calculate with. And this equation here is only the conversion from the units, so from mole to micromole and second to minute, nothing else. If we are already talking about cell culture, I would like to present a calculation for the growth of bacteria. By measuring the OD at different times, the density of bacteria was recorded. When plotting logarithmic here, the ODs, and put them to the time, you obtain this curve here. My tip, Excel will help a lot, because you can use the OD values and just say, well, make this axis logarithmic and everything is fine. You don't have to calculate anyhow. Somewhere in this linear region here, you choose two fixed points. I did this and I called them PT, PT0. You can also call them Peter and Paul, or Mary and Jane, or whatever. My tip is to select these 2 points in a way that you can read an even number on the timeline. So in my example, this is 90 minutes apart. So first you calculate a growth factor, and these 90 minutes are this calculation here, so you can easily write down 90 minutes if you have considered my tip in advance. The other two values are read out here. So you go to PT0 and read this point here and PT and this, and you subtract both of them, divide it, and you get 0.015 per minute. So this is the growth factor mu. Afterwards, you want to calculate the half-life. So what you do, you want to get rid of the natural logarithm. So you do ln2, and this is divided by your growth factor. And if you calculate that, you get 46.2 minutes, meaning that your cell divides every 46 minutes. Using cell cultures is very good to have examples, so I would like to introduce to the calculation of errors. It is given that the true value will always be further restricted the higher the number of samples you have. So what does that mean? Normally in politics, in radio, whatever, you hear, we asked 100 people and they said in percentage something. So in the lab, this would be a lot, 100 measurements. So in the lab, it is sufficient to have 3 technicals and 3 systemic replicates. So what does that mean? The technical replicate is you would in parallel set up 3 experiments where everything is similar. So you have the similar bacteria, similar temperature, similar time when you did it, similar buffers, and so on and so on. Just 3 times what you want to do. And after the bacteria has grown, you measure, and this is the systemic replicates, or you count, let's say it like that, 3 times this solution, 3 times this, 3 times this, and you obtain some numbers what you have counted. So at the end, you have 9 values in your sample. And this is quite sufficient. The area of the Gaussian normal distribution in which 60% of the values are present is called here sigma, or the standard deviation. It is calculated with this formula you see here. You will say, oh my god, this looks very hard, but it is easier than it looks, so don't be afraid. I will explain it to you how it works. First, you calculate your mean value. This is the MVA here. Mean value is you just add all of these numbers and divide it by 9, and this is 14.6 in my example here, and n is the number of replicates you have. So it's 9, so you can describe this 9 minus 1, it's 1 divided by 8, and here the n is the same, you have 9. But what does that mean here? It's the sum. So let's sum it up. What does it say? You have to subtract your mean value from the value you had. So for example here 14 minus 14.6, then this would be minus 0.6. For 15, it would be 15 minus 14.6. It would be 0.4. And all these values for each one, you would square it. Or you can do it like that. You just count 1, 2, 3 times. I have 14, so it's 3 times minus 0.6 square, and add it with here 6 times 0.4 to the square, and divide this by 8. Then you calculate the root out of it, and you get this number that is 0.5 at the end. What does this 0.5 mean? Sigma is found around the true value, so in both directions, so away and to the minus and away to the plus direction from the true value, and therefore this is the normal thing you see normally somewhere. It is of course half plus and half minus, so your error, your delta Z would be plus minus 0.25. In electronic or mechanical work equipment, error limits are usually specified in the operating instructions. For example, let's consider a fictional electrophoresis here. The amps are set in the power supply, and you find a plus minus 1% in your manual, and empirically you determine the changes of the volts at max voltage in your chamber with a measuring device, whatever, and you find that you have differences in plus minus 0.5 volts at different times and so on. Your goal is that if you read out 20 watts in your future experiments, you want easily to calculate the error right away. So to estimate the error, use is made of the error propagation. This is this one here. So what do you do? You divide the delta error by the value, and of course of your watts it is the the addition of all the factors you have to obtain this watts here in my example. So the delta x to x would be, for example, my error in amps, and you can enter these percentage directly because it would be deleted right away if you would have your max amp. So it does not make sense. It makes sense to use the percentage right away, but be careful, it's the plus minus here. So enter the delta, and the delta is from minus 1% to plus 1%. So in the complete range would be 2%, and then it is 0.02, of course. With the volts the same, you have plus minus 0.5 volts, so the range would be 1 volt you have here, and you divide it by the max voltage. You calculate this and you get a delta A divided by A of 0.023. So what do you do if you do your electrophoresis now and you read 20 watts on your power supply? Then delta A divided by A, you would enter 20 volts for the value and multiply it, and you would get this one. So your delta A is the factor from here multiplied with 20 watts, and this would be 0.46. But this is the delta, so remember, so your error would be in both directions again, so it's half in the plus and half in the minus, so it would be plus minus 0.23 watts. So the true value would lie between 19.77 and 20.23 watts, even though the power supply displays 20 watts only. I thank you for listening, and the Serva webinar team wishes you a Merry Christmas. My last tip: if you have no answer to a problem in math, just stay confident and answer 42. Thanks for listening. Bye.